Hi, this is Mohaimul Islam Khan, and I'm a PhD student at University of Texas at El Paso. I'm going to present the final project for one of our classes. It's Computational Mechanics, and the project is called Parametric Analysis of a High-Pressure Combustor to Optimize the Heat Flux. So these are the agendas for this presentation. First, the objectives, then a little bit of introduction and background. After that, the whole design methodology, then results and discussions, and finally the conclusions. The goal of the study was to do an optimization of heat flux for a high pressure Oxy-Coal combustion for a 30 seconds run. And the optimization was done based on parametric and some transient analysis. The tasks were divided into several stages. A transient thermal analysis were done for a 30 seconds run. Then the result was coupled with the transient structure analysis, and heat flux was used as input parameter. The value of the input parameter was varied to find out the maximum heat flux that we can have that will also meet some design parameters, some critical design parameters. So the very first thing that I should talk about briefly is the Oxy-Coal combustion itself. In Oxy-Coal combustion, pure oxygen is used to burn coal instead of air, which is used in the conventional combustion process. And that pure oxygen increases the combustion temperature, so we can have a higher efficiency. And also another parameter to know about the Oxy-Coal combustion is how much heat flux we're getting from the combustion, because that heat flux will determine how much thermal heat input we can put, or how much fuel we could put into the combustion process. So in results, that thermal heat input will determine how much heat generation we can have or how much efficiency we might have. Another feature that can be used in Oxy-Coal combustion system to increase the efficiency even higher is to pressurize the whole thing. There are a few parts of that, like we can have more recoverable latent heat from the combustion exhaust gases, and then we can reduce the flue gas volume. So two very well-known pressurized systems are ENEL and TIPS, and a bunch of studies have been done on them. One of them that you can see on your right is a curve. It's showing how the efficiency goes up with increasing pressure. So for ENEL, after 10 bar, the efficiency kinda gets stuck, and also for TIPS, after 80 bar, the efficiency remains the same. So for my study, I used the 10 bar. So that's gonna be the operating pressure throughout all my simulations. That's how the actual combustor will look like after building. It's a pretty huge body. The length is almost 1 meter. The thickness is 3.5 inch. It has an inner diameter of 11 inch, and the whole body will be made of stainless steel 410. And there are a couple of flanges that you can see on the top and on the bottom surfaces. So these flanges are going to be used to connect the main body with the other parts of the combustor. And not only that, like if we put the combustor on a vertical stand, these flanges are going to carry the whole weight of the combustor, which is almost 2.5 ton. And we're going to attach the flanges with weld on the combustor body. Also, there are a couple of windows on the combustor body, while that we can use those windows to actually see inside, look inside the combustor. And also we can use them to put sensor ports like thermocouple or pressure transducers to get the data. As I mentioned, the material for the combustor body is going to be stainless steel 410, and these are the material properties that I use to do my simulations on. The flange material also going to be stainless steel 410, and we use 300 class. It has almost 24 bolt holes, and the weld height that I'm going to use is 0.5 inch. So that's the geometry I'm going to use for my simulation, and it's only 1/6 of the whole combustor body. The whole combustor body, to design it and to mesh it, it's going to take a lot of elements and a lot of nodes that my student license will not allow me to simulate. Also, it's going to take a lot of simulation computational time, so it's better to slice up a part of the combustor and then put symmetric boundary conditions on the surfaces to mimic the whole combustor body. But it has the window port and then it has the welds, so it pretty much has all the critical surfaces that we want to do our simulations on. And the length is 1 meter, the height, sorry, the thickness is 3.5 inch. So if we put the symmetric boundary conditions, it will mimic the whole combustor body anyways. So the combustor is going to experience a very high operating pressure, weight of the whole body, and a thermal stress. The thermal stress is not negligible because the operating combustion temperature is very high since we're using Oxy-Coal. The curve that you see over here, the orange line, it's how the yield strength changes for stainless steel 410 with temperature, and the green line over here, it's hand calculation based on the hoop stress and the thermal stress equation, and it's to see how the stresses changes with the temperature. So you can see that with the temperature, the total stress goes up where the yield strength goes down. And after one certain temperature, the downfall of the yield strength is pretty rapid. So when I decided the critical design parameters, I was mindful of all this stuff. So after considering a factor of safety of 1.2, I decided to avoid failure. The total stress of the whole body should be equal or lower than 570 megapascal. The maximum temperature should not go above 400 degrees Celsius. But also, we want to maximize the thermal heat input, so we need to find the highest heat flux that we can have, um, and we can still avoid failure. So the analysis types used in this simulation are the transient thermal analysis and the transient structural analysis. And I ran both of them for 30 seconds. It could have been ran for much higher time, but due to the computational time and also the limitation on my computer RAM, I decided to stick with 30 seconds. For parametric analysis, I use the heat flux as the input parameter, and it ranges from 50 kilowatt per meter square to 700 kilowatt per meter square. And as mentioned in the previous slide, the critical design parameters, the maximum temperature over time, and the maximum stress over time are the output parameters for the simulation. So that's how the thermal boundary conditions look like for the simulation, where I put the heat flux on the inside wall and the outside wall is going to be exposed to the environment. So I used convection over there with an ambient temperature of 22 degrees Celsius and air heat transfer coefficient of 22 watt per meter square Celsius. For the structural sections, the inside operating pressure was 10 bar. I used a standard earth gravity to account for the weight. Then fixed support was used on two flange surfaces to support the weight. Then displacement in one of the top surfaces was fixed so that I can have the rigid body constraints in the simulation. The rotation was stopped by fixing the remote rotation boundary condition, and also remote displacement was fixed on two side surfaces so that I can have the symmetric constraints. That's how the structural boundary conditions look like. Operating pressure on the inside surface, and then the displacement was fixed on that surface to provide the rigid boundary conditions. Then gravity was used along the z-axis, and these two flange surfaces were given as fixed support so that they can support the weight, and that two side surfaces, the remote displacement perpendicular to these surfaces were fixed so that it can mimic the whole combustor or can give me the symmetric boundary constraints. So a mesh convergence study was done where the number of elements were increased and one of the critical design parameter, the maximum stress, was observed to see how it changes with the number of elements. So at the lower number of elements, the difference in the stresses are pretty high, but after almost 100,000 element number, the stresses become stable. So I can say that at 100,000 or after 100,000, the mesh converge. So um, I decided to go with a mesh number somewhere around there, somewhere around 130, because that will save me a lot of computational time, and also it will give me a better quality result. That's how the mesh looked like in my study. The number of elements I used was around 130,000. The number of nodes were around 450,000. And these are the options that I used for the simulation. The physics preference was mechanical because I'm using structural and thermal. So the size function was curvature. I used find relevance center to get a better mesh. And as I mentioned before, that the critical section for this simulation were the hole and the weld. So I had to use finer mesh in these sections than the other body parts. So I used 10 times higher number of the elements than the other body parts on these critical sections. Finally, the results and discussions. A bunch of heat flux values were used as input parameter for the simulation. And that's a result of one of the design points, 250 kilowatt per meter square. The animation that you see over here, it's a 20 frames animation, and it compresses the whole 30-second transient thermal analysis result. As you can see that the inside surface, it sees the highest temperature. It makes sense because I put the heat flux in there, and also the temperature increment, it starts from the very bottom surface and it starts to go up. However, it's only a 30 seconds run, and the thickness of the whole body is pretty huge, so the outer surface doesn't get that much affected by the high temperature at the bottom wall or the heat flux. Also, throughout the whole time span, the heat flux is constant on the inner surface, and it kind of gets accumulated over the time. So as the time goes up, the temperature, the maximum temperature goes up as well. And for 250 kilowatt per meter square, the maximum temperature that the inner surface is facing is 171 degrees Celsius, which is pretty below than 400 degrees Celsius, our critical design parameter. After the thermal analysis, the results are coupled with the transient structural analysis. And the result you can see over here is a von Mises stress for 250 kilowatt per meter square. And as I mentioned before, that the critical area of all the body parts are the optical portholes and the well sections. The simulation kind of shows the same thing as well. We have the maximum stress concentration in these corners of the holes. It makes sense because the whole area has the minimum material of all the other areas. So the stress, which is the force over the area, goes up for this whole section. And also these flange surfaces are kind of holding the weight of the whole body, and they are connected with the main body with these welds. So the weld section will see some stress concentration. It also makes sense. In the transient analysis, we saw that the temperature goes up with time, so thermal stresses goes up. As a result, over here we see that the total stress goes up with time. This is the result for the total deformation for 250 kilowatt per meter square. And as you can see, the deformations are pretty negligible. They're on 0.15 millimeter scale for this whole 1 meter body. Um, the deformation starts from the middle, which makes sense because there was no support in the middle. However, the maximum deformation the body sees is on that corner. It also makes sense because I fixed that section, that face, to get a rigid body constraints. So all the previous result slides showed us a general trend of the results, like which surface is going to see the maximum temperature, or what areas are going to have the stress concentration or maximum deformations. Now we're gonna look at the critical design output parameters that we're gonna have for all the input heat flux values. Um, as I mentioned before, that the two critical design parameters for my case are gonna be the maximum temperature over time and the maximum stress. So I plotted the maximum temperature over time versus the increment of heat flux. And as you can see that with the increment of heat flux, the maximum temperature over time goes up, which kind of makes sense. Uh, for all the points except the 700 kilowatt per meter square, the maximum temperature lies below the critical temperature, the 400 degrees Celsius. For 700 kilowatt per meter square, the maximum temperature after 30 seconds exceeds the critical temperature. So I can say that the optimized heat flux value has to be below 700 kilowatt per. So this is the result for the maximum stress over time against the heat flux. And that was the second critical design parameter. If you can remember from the earlier slide that the maximum stress cannot go above 570 megapascal for stainless steel 410 combustor body. And you can see from the curve that as the heat flux goes up, the stresses goes up. And for all the values above 250 kilowatt per meter square, all the heat flux gives a stress, a maximum stress, which is above the critical stress. So it kind of lets us with only four values, the 50, 100, 150, and 250 kilowatt per meter square. And as the last optimization criteria suggests that we should take the highest heat flux of all the eligible values. 250 kilowatt meter square is the one that kind of meets all the criteria. The temperature for 250 kilowatt per meter square doesn't go above 400 degrees Celsius. The stress for 250 kilowatt per meter square doesn't go above 570 megapascal, and also it's the highest heat flux of all the heat fluxes that we have studied. Uh, so for conclusions, the objective of the study was to find out and optimize heat flux for a pressurized Oxy-Coal combustion. The simulations were done for 30 seconds of combustion. I did a transient thermal analysis, and then I coupled the results with the transient structural analysis, and we saw the maximum temperature values, we saw the stress and the deformation results, and several heat flux values were used as input parameter to do an parametric analysis. According to the simulations, the highest stress concentrations areas are the weld and the pore hole areas, and the inner surface was the area or the surface that's gonna face the highest temperature of all the other parts. Several optimization criteria were considered, like the total stress, the maximum temperature, or the highest thermal heat input. So of all the heat flux values, 250 kilowatt per meter square was found to be met all the optimization criteria. So that's the end of the presentation. Thank you for your time and concentration.